Let's solve this fucking circuit, and this thing is going to make it a lot harder than it would usually be because dependent sources suck. Well, the way we can think about this, right, we want to find this current here. Well, we kind of need to do the whole Thevenin thing to actually analyze it. So let's start with redrawing the circuit like this. Actually, call this R Thevenin, and here we go. So that's what we want to do. We want to redraw the circuit and find the Thevenin resistance. We need this Thevenin resistance, but real quick, let me just state why we need it. Well, I of t, it's going to be equal to this, right? Where we go I infinity plus parenthesis I of 0, leave minus I of infinity d to the negative t tau, where tau is what? Tau is L over R Thevenin. So that's the whole reason why I need to find R Thevenin. Okay. Now, you can't just find R Thevenin like this, right? You can't, damn it. You need to actually go one step more. So instead of writing R Thevenin here, I mean, R Thevenin is there, but we have to insert an artificial source to actually find things. So we'll do a plus, a minus, and we'll do a 1 volt source. So VO is equal to 1 volt. Okay, so contribute this voltage will shoot out, it will source a current. This current's going to go in these two directions, and look at this. Okay, this means this is a super mesh. With this dependent source in here, we have to analyze this as all if it was a super mesh. So we'll write super mesh. And if it's a super mesh, what do we have? Well, we would have this current I, little I, would have this current I2, right? So if you recall, super meshes work. So okay, first off, we have it's going to be equal to 1 volt, right? 1 volt is going to be equal to 40 I2 plus what? Then plus 10 I1. Not I1. We'll just call it little I. Okay. So this is the equation that describes this super mesh. Yeah, this is not that useful because we have one equation, two unknowns, so we need one more equation. So then let's say I like to treat this, I like to analyze right at this dependent source, in my opinion. Or you could say right here, right? You could just, I mean, it's whatever helps you think of it better, but truly we're analyzing right here. So, and I'll call this Vx. Okay, at Vx, what do we have? Okay, well, we have I1 going into it. I1 going into it. And then down below it is the 0.5I. By the way, it's not I1. I don't know why I keep saying I1. I. And then we got I2 coming out. So in other words, it's I. So this will be the in, right? And then this side will be the out. So in is equal to out, right? That's the rule for the Kirchhoff laws, Kirchhoff's current law, right? 0.5I plus I2. So now this is good because we can use this. We have two equations, two unknowns, and we can now solve. So let's just say that let's rewrite this all in terms of I. So I, if we minus this I on the other side, we just get 0.5I is equal to I2. Okay. So now we can go like this. We can insert this information into this equation and solve. So it'll be 40, and I'll substitute this in where I2 is, so it's going to be 40I 0.5 plus 10i. And that's going to be 20i plus 10i is equal to 1, right? So 30i is equal to 1. What is I? I is equal to 1 over 30. And there we go. Now, big conceptual idea here is that this I is not this I. This is a Thevenin circuit. I mean, well, not really, but this is a different circuit. We're trying to find the Thevenin equivalents here instead of this circuit. This is a completely different circuit. So even though this is I and this is I, it's the same variable, but it's actually different because this is a different circuit than this one, okay? And I've always made that mistake where I thought they're the same, but they're not because we inserted an artificial source, right? We inserted an artificial source. Artificial source current. Okay, so a big conceptual thing happening here. Okay, thus, okay, now we can actually you find our Thevenin, where our Thevenin is equal to what? It was equal to this guy, and this is just Ohm's law here, divided by I want to say I artificial, right? What's that? That's going to be 1 divided by 1 over 30, which is just 30 ohms. Okay. So now, all of this for really this one piece of information is a lot of work just for some resistance. Okay. So now we can find what tau is. So tau is equal to L over R. And L is 6, so it's going to be 6 over 30. And we can see that tau is 1/5. Okay, that's good. And units for tau is seconds, by the way. It's a time constant. Okay, so almost done already. Now we just have to think about what I infinity is. Okay, so, oh, did not want to do that. I infinity. Now, the way you can actually think about this, there is going to be no math for I infinity because it's just 0. Now, you're like, how is it 0? How do you know it's just 0? Okay, look at this. So there's resistor, inductor, and dependent source. So over an infinite amount of time, right? As infinity goes on forever, okay? Eventually, these resistors will deplete all the energy and there will be no current. Everything's going to get dissipated into the resistors. So I infinity is equal to 0. And that's a conceptual idea. Now, real quick, if this was a capacitor, same thing would happen. The VC, the voltage for the capacitance over an infinite amount of time, if it was VC for the circuit, it would be 0, right? Because all the energy would get dissipated into the resistors. Okay, so now we can actually import all this information into our equation up here. So I of t is equal to what? Okay, it's equal to 0 plus, and they said I of 0, so they did give us a nice little piece of information. I of 0 is equal to 2. And what else did they give us? So I of infinity, oh, well, we found I of infinity. It's 2 minus 0, e to the negative t over, and tau is 1/5. So we'll clean this up, we'll write it as 2e 5t. And don't forget your negative sign there. Okay, and since this looks kind of messy, let me just edit that real quick, make it, oh, damn it. Did not want to do that. Let me just clean that part up. There's a parenthesis right here. Sorry, that was kind of a ugly writing here. But yeah, this is your answer. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up in the algorithm.